Now back to our problem. We're here. Okay, so we know pretty much everything. Do we know the radius?
25.
Yeah. It's half the 50, spot on. So we will just write this down. So we have dv dt is 100. So going from here, let's write this arrow, therefore 100 equal to dv dr is 4 pi r squared. We know the radius is 25, and then times dr dt. Question is, what's the dr dt? How fast is the radius of the balloon increasing? So, how do I get rid of that number? Divide both sides. And again, I'll go with the decimal places. Dr dt equal to divide both sides. What did you get? Okay, this is okay.
0.27. No, 0.0.
0.01273. I recommend the 4 significant figures, so that's what I mean there by 4 significant figures. I think the engineering are happy with 3. 2 probably isn't enough. And units.
Centimeter per minute.
Centimeters for this?
Yeah, per minute. Yeah. Second.
So, distance, time, centimeters, seconds. The other one is very similar, so I'm going to skip that one.
All the way. If you said 4 significant figures there, if you had like 1273 point and another 4, like, are you only counting 4 figures?
The first 4 not 0, yeah. So
yeah, so like if it's a big number, you're only counting 4 figures of the whole number.
yeah. Now it's not something I'm going to be strict with. Now I'll do the 4. You'll see it later on in a section where if you've got a big number, especially we're going to have things later on where we've got error involved. So you can't really be that accurate after a while anyway. So say if I've got say 12,000 356.241. Now, perhaps it's just going to be, it might be just more natural to say 12,356 as correct to 4 significant figures, but actually the way you would do it is the same. You take the first 4 and then round after that. So you'd actually take 1, 2, 3, and would you round that?
No.
5, 6, up, 6, and then just put zeros after that. Now obviously I don't leave it like that, but a 0. So that would be that rounded to 4 significant figures. I wouldn't say it's something to get hung up about though, at the same time. Yeah, but that is how you would do it. That's the extreme one. It seems a bit weird, but actually it's not too bad. I mean, if you had someone had that kind of amount of money in the bank, they wouldn't. I'd be happy too myself. You wouldn't say that. You know, you probably just 12,300. Be more after that. Okay. Now this one, this last one is almost. It's probably harder than what I would give you, completely honestly. But it's a good one to do because it shows you what happens when things, if you went slightly wrong. If you didn't take the most complicated thing, this kind of shows you how we get out of it. So here we've got area. Oh, sorry, I'll allow you. What are the 3 variables?
Area, radius, and time.
And?
Radius.
Yeah, that's 3.
And rate of change.
Rate of change of area, rate of change of radius. There's something else knocking around. Volume. You've actually got 4. And you can still do it. The thing, the intuition kind of, that I didn't really go near really, just that writing it out will still work. So you're going to differentiate the most complicated thing with respect to time. Now I'm going to kind of push it one way, but if you get it wrong, we will be okay. And something else will go wrong anyway, I think. What do you think is the most complicated thing there?
Volume.
Volume. If you go for area, it's fine.
Will you get? Can you actually get rid of one and use the other? Is that what you're getting
You
at?
can. There is a way you can do this kind of simultaneously. So you can do 2 of those kind of equations. But actually, I'm going to do it all in one go. All in one go. And actually, we're going to get the answer more or less straight away. So, so say 2 options. Well, we're just going to go for one option. And really, it's just show us something else. So, you chose volume to be the most complicated, and I'm going to go dV dt. And I'm going to go dV, and I'm going to do gap dt. And now what you have to do is put in dA, pair of dAs and a pair of dRs. Unfortunately, you can get it slightly wrong here. So, first one, dV dA or dV dr?
VDA.
Okay, dV dr is the one to go for, you're right. dV dA, it's going to be difficult. The rate of change of volume with respect to area. You can actually do it, but it's nasty. As I said, this question is harder than I'm going to throw at you, but what we have to do in the middle of this is what I want us to see. So you're going to do dr. And then put dr there, and then do the dA. I think you get in trouble if you do dVdA. You'd have to split the dVdA into maybe dVdr, dRdA again. Okay. The surface area is increasing at a constant rate, okay? We'll go back to that in a second. We're just looking at this at the moment. Is dVdr any problem?
No.
No? Differentiate volume with respect to radius, no problem. dAdt, is that something?
Yeah, it could be. We have DAD actually, 500.
It's what does dAdt represent?
The area.
The area represents
More specifically,
the change of area.
rate of change of area. dRdA is a bit funny.
Yeah.
Okay, so this you could get something like dRdA in the easier questions, and this is what you have to do with them. So you got dV dr. You have dA dt. They're normal kind of things. Can you recall what we're going to do with this dRdA?
1 over dA dr.
Yeah, you can flip it and make it 1 over. So that could happen here if you did dr dt instead of dV dt. dV dr isn't a problem. If we know the radius, do we know the radius? Yeah. dA dr isn't a problem. Well, I have to write up some formulas now because we need the volume of a sphere is 4/3 pi r cubed, and the area is 4 pi r squared. And now we just have to stop for a second. What are we actually looking for in the question?
Find the rate, increase in volume.
Correct. What's the
So that's dVdr, is it?
dV dt?
DT.
dV dt. So this is what we're looking for. And dV dr no problem. 1 over dA dr no problem. Do we know dA dt?
No, we're looking for it.
No,
Oh, sorry.
the area of the sphere is increasing at this rate. So this is dAdt. Right. So we've already differentiated this a few times. You get 4 pi r squared. 1 over dAdr. What's the derivative of 4 pi r squared with respect to r? 8 pi r, yeah. I'd be probably saying 4 pi multiplied by 2r, 8 pi r. And then the dAdt is 500. And do we know the radius? 30. Yeah, 20, sorry. So we'll sub that in. Well, this one will get an exact number, I think. 4 by 20 squared divided by 8 by 20 by 500. And it's coming out as 5,000. Units. Go again. Per second is good. It's a rate of change.
Centimeters cubed, is it? Centimeters cubed?
Centimeters cubed. This is volume per unit time. Centimeters cubed per second. It's probably not a more natural question. Really, would be that you know how much the volume is increasing because you're pumping air into it, and you want to find how much the area is increasing first. Theoretically, there'd be probably some reason to do with maybe advanced elasticity, whatever.
Did we have to use the area though? Could we just skip the area altogether and just use the volume, the time, and the radius as the three variables, like?
No, because, well, I'll write down the start of the other approach. So I'd say volume radius, yeah, volume radius time, yeah. So you get dV dt. The other option, by the way, is two formulas. So dV dt equal to dV dt. And now I know you just want to use this, but give it a second. dA dt equal to dA dt. And then put in both cases dr dr. You're proposing to use this. Having a little look at the question, what are we looking for in the question?
The rate because of volume when the radius is 20 centimeters.
Rate of change, so what will that mean, all these symbols?
So dV dt, like.
So this is the question.
Yeah.
Any problem with dV dr? No. What about the RDT? You have the radius, but have you got the rate of change of radius? No. You don't have enough information.
Can't you just differentiate twice the volume?
There's probably something funny you can do, but that would probably indirectly use the area.
And then more.
It's definitely more complicated.
Okay.
What does it mean? It just means that you've got a volume increasing, and you know nothing about it if you neglect a piece of information about the area. You needed that piece of information.
Okay.
Right. So that's a little section. The likelihood is that this will be on your test and not on your exam. That's I shouldn't have given that hint, but I did. Right. But it will be on your test. Okay. Right. Okay. Now we're going to start confusing things. Right. Page 118. So we had these partial parametric curves. So there was like a parameter t, and for each value of the parameter t, there was two little equations, one for x, one for y. You put the t into them, and you get an x and a y. Put them together, and that's a point. So each point on the curve corresponds to, think of it as a point in time. Imagine just something tracing out the curve. And that's one type of curve. It's different to the graph of a function. And now we're going to look at another way of forming curves. So a lot of the times when I was going on about the car designs and other things, actually that were these types of curves. Okay. So for example, the shape that's made by a window is one of these types of curves. Now, to be honest, most of them, if you can do them like this, you can do it the other way. That's probably the truth. Okay. So suppose you get if you have an equation. So there's a phrase that you meet in school in maybe second year or something. They go on about the equation of a line, the equation of a circle. And I don't think they quite exactly explain it fully. Now we're going to try and explain it fully. So if you've got some equation, so I'll write it like this, and then there's two examples down there. So what this means is just some formula in x and y equals 0. So for example, take away the 2x plus 3 from both sides, and you've got y minus 2x minus 3 equal to 0. It's out that form. Or take away the 16, x squared plus y squared minus 16 equal to 0. It's out that form. And now I will explain the very long explanation of this in the weekly summary. But what we do is we take solutions of this, which will be a pair of numbers. So give me one solution of this.
X is 3 halves. 3 over 2, no? Minus 3 over 2. X is.
Should be two numbers.
That's fine.
Loads of them. X is 0, y is 3. X is 0, y is 3. So 0, 3 is a solution of this equation. Plot all the solutions. This can be plotted, can't it? Yeah. Plot all the solutions out of an equation and you get a curve, some kind of a shape. This one, if you plot all the solutions of this, you get a straight line. And this one turns out to be a circle. Have we any point on this? 4-0, for example. Okay. So the equation of a curve basically asks the question. So what it is? Find all the solutions. Now you don't actually do that. There's infinite. It's kind of more a theoretical thing. You have an equation. Imagine all the solutions. Plot them, and then you get a curve. And this is the start of what's called algebraic geometry. You have algebra here and a picture here, algebra geometry. So basic thing is solutions to equation, points on a curve. Solution of an equation corresponds to a point on that curve. Solution of this equation corresponds to a point in the curve, and take all of the solutions. So we'll take two little ones here. So y equal to 2x plus 3. If you plot all the solutions, looks like this. And say the other one there, x squared plus y squared equal to 16, you can show that it is a circle of radius 4. So we'll just throw 2 points down, 0, 3, and 4, 0. And then there's other things you can find where the intersections are. And then if you go mad into this, I can go as mad as you want into this, but say you could imagine you've got two equations and you're solving the simultaneous equations. So there could be a simple question, solve the simultaneous equations, but a more interesting one would be, how many solutions can there be? And you might have no solutions, 2 solutions, 1 solution, this kind of thing. And that would be geometry answering algebra questions. Going too far, I'm just indulging myself there. Okay, so write down the equation, plot all the solutions, you get a curve. What might these curves look like if we zoom in? Straight lines. Therefore, what do they have? Tangents. So we have questions about